Welcome everybody to this next edition of the SMP Power Hour. And today we're going to be talking about ignition coils. Now, ignition coils are, the heart and soul really of today's modern ignition systems. But there's a lot more that goes into it, primarily the triggering. Does the cam and crank sensor have the proper inputs and send the signal to the PCM, and does it reach the ignition coil properly? And what does the ignition coil do with it? Chris Jongsma here today is going to be our guest presenter. He's one of our training developers. He comes to us with an extensive background as a technician and also as a mobile diagnostic technician. And he's going to share some of his experience and real life scenarios here as he diagnoses vehicles. And so throughout today's presentation, we're going to learn about 2-wire and also 3-wire ignition coils and how to effectively diagnose them. Quite often when we look at ignition coils, we see what's on the outside, but we're not really sure about what's on the inside and the windings and all this great stuff. And how does it really work? Chris will share that with us. Many people for many years have been familiar with Standard and Standard Motor products. Standard's been around since 1919, so we're coming up on close to 104 years now. And many people have known them through the years as Standard Ignition, or also maybe even recognize the Blue Streak name here and what it means as far as quality. And we've got an extensive line of new, improved, enhanced ignition coils in the Blue Streak line there. But one of the key differentiators here with Standard is a commitment to manufacturing as well as testing. We've got engineering test facilities all around the world looking to continuously improve our products. Here at our corporate training center in Irving, Texas, literally across the wall from our studio here today, we've got a group of our engineering test technicians actually installing a whole slew of ignition coils and testing them to ensure that they are performing as we expect. So it's a great timely presentation here. We continue to do analysis to ever improve our product, delivering to the technician a name brand that they can rest their name on. With no further ado here, I'm going to turn it over to Chris. A great presentation on tap.
Thanks, Ryan. Welcome, everyone, to our Power Hour class on ignition system diagnosis. Some of the topics we'll be covering will be ignition coils, the breakdown of them, the various types that we'll be diagnosing, how these coils are controlled, looking at some wiring diagrams for the PCMs to the coils. We'll even be throwing a case study in that I've done, and also analyzing lab scope data from ignition events. Now here we're showing a picture of some of the test equipment that we may be using when we're testing ignition events. One basic test equipment would be a spark tester that we see on the left side of this picture. This is going to show us the spark event can travel a gap, and also that we've got good, clean, strong spark. This is a good stress test for a coil also. So this is one of our basic tests that we should start off with. And we've actually placed this on a 2010 Dodge Nitro in the shop right now. So we'll start this vehicle up and look at what this looks like with a spark tester hooked up to the vehicle. Here you can see with the vehicle running that we've got a good clean spark. It's strong and it jumps the gap easily. So now in this case, we can shut the vehicle off and we know that we've got good spark here. Now, in the instance of not having spark present when we've done a spark tester, now we're going to need to dig further into why we don't have spark present. This would include testing the ignition system with a lab scope and analyzing wiring diagrams. So some of the coils that we see on vehicles now range anywhere from a simple 2-wire ignition coil, where you will have a battery feed to the ignition coil and the PCM grounding the other side and controlling everything, all of the way to a full coil pack with a module included. And this will have a much different control to it. So again, if we start off by looking at a 2-wire ignition coil, this is going to be one of our more simple coils and probably one you're familiar with. Both of these are from Ford products and often replaced too. So with these ignition coils, they're often under a really high amount of stress, and they're normally controlled solely by the PCM. So if we look at a little bit of a breakdown of the internals of this ignition coil, we are going to see the primary and secondary windings in it, a permanent magnet, and an isolator. So most all of the ignition coils are going to have a similar breakdown internally with these components here. However, testing them when they vary with including ignition module and other things, then testing diagnosis will change. Now you can see in the slide here too, we've placed a paddle probe on top of the ignition coil. This is going to give an ignition voltage waveform. And with a 2-wire coil, this is generally an easily accessible spot for many of them. And also it's a pretty reliable waveform that we could do when we're testing. So now we're going to go back to the 2010 Dodge Nitro that we have in the shop. And this actually has 2-wire coils on it. And we will be viewing a current waveform and also putting a paddle probe on the coil to get the voltage waveform as well. So we'll start this up. And now we've got our low current amp clamp on the battery feed to the ignition coil. And then we've got a paddle probe that we're going to be looking for that voltage trace with on the ignition coil. So if we solely look at just the current waveform now on the lab scope, we can see we only have one trace showing. And with that current ramp, what we're seeing is the coil building amperage and then a nice clean shutoff and ignition event happening. So now to see the voltage side of this, we'll put the paddle probe on the ignition coil. We'll place it on the coil. And if we go back to our picoscope screen, we'll now see that we've got a good voltage signal. I'll remove the paddle probe. And you can see that we have nothing there. Put it back on the coil, and we've got a good voltage signal in this case. That's what that testing looks like when we're hooked up to that vehicle. Now to get a better look at what's going on here, we'll go to the wiring diagram for any 2-wire coil essentially. We're going to have a fused battery feed to the ignition coil. So that is going to be our power feed to the coil. Now you're going to have either the PCM or the ECM controlling the ground side and making this ignition event happen. So if we look at this a little bit closer, again, the beginning of the current ramp or in this voltage signal here, we are building up a dwell inside of this ignition coil, and we want to ramp it up and build energy in this. And then we are going to have a clean, sharp cutoff to that. And then that's when our voltage spike happens. And that's when our spark event happens. Now, one thing to keep in mind too, is if we are going to be looking on the voltage side of a 2-wire coil, and we want to see what this ignition pattern looks like, it's going to be a high voltage. And such a high voltage that oftentimes it's an unsafe voltage for our lab scope. And in that case, what we've got here is a picture of the attenuator, which would then change that input voltage to a lower range. So if it's a 20-to-1, 20 volts would equal 1 volt. And then we can get that voltage into a viewable range into the lab scope and not damage our lab scope. So now that we know a little bit more of what's going on internally with this ignition coil, again, of how we first build energy through the windings, and that we store energy in this ignition coil, we then are going to cut the current and we'll have an induced voltage, and then that's when we have the firing event. So let's hop onto that vehicle one more time and look at these waveforms again. So we'll start the vehicle. Now, once the vehicle is started, we will again have the current clamp hooked up to our battery feed. We will have our paddle probe, and you can see how we've got the design on there. That tells us to place it on the ignition coil. We now have our voltage waveform on the second channel, and we can see how we've got a clean turnoff, and then we have a firing event on the voltage side. So that's what that will look like when we're analyzing it with a lab scope. Now, one of the driving factors, though, of this, again, is either the PCM or the ECM. So this is going to be determining when these ignition events occur and for how long. So the PCM will reference other engine data, such as timing data, crank or cam signals, to determine when to fire an ignition coil. Now that we've covered some of that, let's dig into a case study that I performed. So when I was on the road, I would oftentimes diagnose a vehicle that was already into another shop and they had already tried to perform repairs and address a customer concern, and sometimes they couldn't fix it. And so then I would be called to try to diagnose the vehicle. Here we've got a 2015 Ford Edge with a 3.5 V6, and it has just over 75,000 miles on it. So the customer concern was that the engine will stumble under load, and one shop had already replaced the spark plugs on it, the number one ignition coil, and the number one fuel injector. So one of my beginning steps, though, is to actually verify this concern. So we ran the vehicle at idle, and what I noticed was that the vehicle seems to run normal at idle, and the condition doesn't seem to be that present. However, when we actually accelerated with the vehicle, I could feel the misfire, and also I could recreate this by power braking the vehicle. Another thing to make note of here too was there were no warning lamps on this vehicle. So following that, now we've kind of got an idea as to what's happening with the vehicle. Feels like it's misfire. Why don't we perform a pre-scan? During this pre-scan, this is with the Ford factory IDS scan tool. We pulled a P0301 cylinder 1 misfire. So it looks like the other shop was kind of on the right direction, that they knew the cylinder that they should target. But let's take some further steps and see what they might have missed. One of my first steps of determining what could cause this would be doing what we call a power balance test. Now, this power balance test is going to tell us each cylinder's contribution in relation to the other cylinders. And so in this power balance test, we can see that we have a blue trace for what's currently happening and a gray trace for history events that have occurred.
Hey, Chris, sorry to cut you off here. One question just came in and says, how is the tool determining that line, those lines, or what's being used here? You know, some mystical magic? Yeah.
That's a great question. So in order to reference this and determine what cylinder has low contribution or how these things fall into place, it's actually viewing the crankshaft signal, and we have to know that the position of this in order to time these events. So because this PCM is driving these events, it's using the crank signal and also accelerations and decelerations of the crank signal speed. So if we have a sudden deceleration where a cylinder is not contributing, then we will see that slowdown in crank speed with a crank signal, and we'll then know position of what cylinder is not contributing.
So it's pretty amazing. I mean, that's happening very quickly. I mean, microprocessing here, and I'm assuming, I know your next slide, but that same technology is going to be used for the power relative compression test also, right?
Very true. Yep. So let's move into this next slide and we'll see what I was doing here. So here we've got what is a relative compression test with the IDS scan tool. So with this scan tool, it'll do it for us where it'll disable fuel so that we can actually have just a cranking event and see what the contribution is mechanically of each cylinder. Because now we want to determine, is this going to be like a fuel or ignition event, or is it going to be a mechanical failure? And is it obvious enough that we could start going down that route? So in this case, they all look very similar. We have one that's 1% off. This is not a notable difference or anything of concern at this point. So now that we kind of have track of that, we have a cylinder 1 misfire for sure off of our power balance test, and that the relative compression of the mechanical state of the engine seemed to be good. I wanted to view the fuel trim data, and you can see here that the fuel trim data looks pretty close to 0. Now, this is an important point to make, because if we have a fuel control issue, such as a fuel injector, our fuel trims are going to be skewed quite drastically, and that's going to lead us down the path of something like that. However, with an ignition misfire, that is not going to affect our fuel trims very drastically. So now that we've taken those steps, my next step here is now pulling a wiring diagram and making some testing of these ignition events and seeing what we're running into. So again, we've got a power feed and we've got a fused jumper at the power distribution block and in place of the fuse, and we've got the low current amp clamp on there. This will give us our current ramps. And then also we have a ignition probe hooked up to coil 1, since that's our suspect cylinder. And then we have a known good reference, which will be coil number 5. So we have something to compare to and see what might be happening in our suspect cylinder. So here we're comparing our known good against our suspect cylinder. So in our known good, the cylinder number 5, we can see that the current of the coil ramps up nice and clean. And then we have a very sharp, abrupt shutoff. And that when we do that, we have our ignition kick then, and we have a good sharp voltage difference. And so if we look at our cylinder 1 waveform, however, we can see that current does ramp up, but then there's not a good clean shutoff though, and it's kind of glitchy. And in doing so, then we also see that on our primary side though of the voltage, where again, we don't have that spike because we don't have a sharp turnoff. Now this, we've already done a coil, we've already done a plug, we've already tested everything else, and now we're even looking at the control here. So essentially what we're looking at is from the PCM. So in this instance, this is going to be the PCM that's faulty, and we need to replace this PCM because it has a failed driver internally and not cleanly making this ignition event happen. Now, some portions to installing this PCM, you don't just replace the PCM. We have to program the module with the latest calibration. We have to do a security parameter reset. We have to do a neutral profile correction. And we also have to relearn the transmission strategy.
Chris, please explain a little bit more about the neutral profile correction and also the transmission strategy and why that's important.
Yeah, those are both great questions. So the neutral profile correction is going to be sometimes worded a crankshaft position relearn. So as we were just talking about earlier, we're determining misfires off of that crankshaft position signal and also accelerations and decelerations of that in order to determine misfires. So we now need to relearn this profile of the crank signal to this PCM so that it knows what is known good, and then that way we can determine misfires. As far as the transmission strategy goes, we've got the tag shown here on the bottom left. And this is going to be numbers that are associated with the solenoid body in the transmission for shift strategies in the trans. Now, if we don't program these, we could have delayed shifts or harsh shifts, anything along those lines, and damage something. So one key point to make of this too is this tag is oftentimes hard to see. It can be under coolant lines, airbox, piping, stuff like that. It's not easily accessible. The other thing is that the tag could be damaged or even missing. So one key point to take away here is that we should exhale the trans strategy out of the original PCM. Since we didn't have any communication issues or anything, we basically just had an ignition coil driver fault. So we'll take the trans strategy out of that PCM, and then we will put it back into the new PCM that we're replacing.
So that might account for those times when somebody does something like replace the PCM or replace the transmission and doesn't do that relearn, right?
Exactly.
Hard shifting. And back to that neutral profile question that came in from Bob there, you know, how often don't we see it where we've got a P0300 random misfire code, right? I mean, somebody's probably done something and didn't do that crank relearn or the neutral profile, depending on the manufacturer's nomenclature of it. But the PCM just doesn't know what to look for. And so that's where we get the unidentified one. Even mode 6 doesn't necessarily help. You know, this example, the scan tool did help, but these are all important procedures. And I just want to reiterate what you mentioned here because they're great points. And quite often as technicians, we don't always follow all the instructions until after something didn't work.
Yeah.
Right.
Another good example, even outside of Ford, would be GM. They oftentimes will set those random misfires where you get a P0300, a random misfire code, and then you go to look and it looks like all the cylinders are kind of misfiring a little. And oftentimes that is from not a crank learn not being done on the vehicle. And so once again, it's a really important step. So we have a point of reference.
One of the questions came in from Rick here, and he's asking about, he doesn't do module programming. Can you do that with a scan tool, or what's really required with that one?
Right. So that's a great question. So an aftermarket scan tool is generally not going to have the programming capabilities that we need. And so either a factory OEM scan tool would be needed to program a module and set it up fully, or what we need to do is have an aftermarket scan tool that's capable of utilizing a J-tool device, so a J2534 compliant device. And then we also need a OEM subscription alongside of that. And then we have access to the programming features we need in order to actually program that module. Sometimes in our aftermarket scan tool, we may have some of the setup procedure after of a crank relearn or something like that. But that would be more items of finishing up a programming, not necessarily the programming itself.
Good to know.
So now on top of this topic, this is moving back to that Ford PCM replacement again. You may have run into that where you've had a burnt out driver in the PCM and replaced a Ford ignition coil. A power tip that we've got though is to replace all 6 coils or however many coils are on this vehicle. And this is going to protect the new PCM that we just installed. As we saw in the wiring diagrams that we looked at earlier, there is no safeguard in between any of these devices. So if one is getting stressed an awful lot, then we're going to put all of that right on something else again. So we've got to think if one coil failed here, could happen again with another one as well.
So Chris, to reiterate and kind of cap off that case study, so you were called in after they've already replaced a fuel injector, ignition coil, and a spark plug. So we need ignition, we need fuel, we need mechanical. You verified really all that stuff. We need timing. But you went one step further and determined that it was a triggering issue, right, at the PCM,
exactly.
From the PCM to that. So while some of these main components were replaced, it's even further. And it was
yes, exactly.
Module processing piece. Would you mind going back to that wire schematic of the 2-wire coils earlier? I think there's an important tip to be said here also, like when you hooked up that current probe, yeah, right there. If we place that current probe closer to the fuse, and you kind of did that in this case study, we can now watch all the ignition coils.
Exactly.
Right?
So if we look at this diagram a little closer, we've only highlighted a section of this power feed to the coil in red, just for clarity's sake, so you could actually see it. But that's all a violet wire. That's the power feed to all of the ignition coils. So that's going to mean if we go to the right of that splice, the S136 there, we will then see anything that's happening in that circuit as far as current. So we will then have what we sometimes refer to, and many techs might remember from the old sun scopes or something like that, where we have a parade pattern. So now we're going to be seeing the current ramp of every ignition coil on the circuit. That'll also give us, if we're missing one, then if we do the voltage of one of the coils, we now have our sync, if you want to call it that, and we can now have a point of reference as to what coil may be failing.
Excellent explanation. Thank you.
All right, so we'll scroll back through that case study again. And now moving on from 2-wire coils, we're going to move into diagnosing 3-wire ignition coils. Now, with adding some more terminals to these coils, we're oftentimes going to have an ignition module internal to the ignition coil. So if we look at a more dissected view of this ignition coil, we can see now that we've got the ignition module in there. And to the left here, we've got a GM ignition coil, and we've even got a heat sink on top of this. So now our testing procedures are going to change from the 2-wire testing to the 3-wire. Let's look at what it would be to see the wiring diagram on this Honda 3-wire coil. So we've again got a battery positive feed, the engine ground on the gray wire, and then the yellow is the PCM control, but it's controlling the ignition module that's internal to the coil. So in this example here, the PCM contains programming for basic ignition timing events for various speeds, map pressures, and then it also even adjusts ignition timing according to engine coolant temp and intake air temp. These controls are all going to occur on the yellow wire though. So we're going to look at a Toyota 3-wire diagram as well, because we're going to do some testing on a vehicle that we've got here. This is going to be on a 2022 Toyota Venza, and the ECM is again going to be the triggering device of this circuit. We will have a battery feed on the green wire. We will have ground on the white and black, and then our ECM will be on any of the other wires that we're showing here. So the coil looks like this right here. Now, as far as lab scope setup goes, we're again going to have a current clamp on the battery feed, and then we're going to have a voltage probe placed on the PCM control of the ignition module internal to the ignition coil. So let's go on the vehicle now and look at these setups. We have our ignition probe placed on the PCM control wire. This will be a 0 to 5 volt signal. And then we have our low amp clamp on the battery feed. So now we've had this signal running on the Pico lab scope here, and we'll go to this waveform. And so we've just paused this waveform now so we can analyze this a little closer. The current ramp you can see is similar to the previous one that we just analyzed. You can also see we have current limiting happening here. So we don't have just a clean peak. It's actually built up enough current and it's limited it, and we have that clean shutoff. Now you can see our voltage is going to look different than on a 2-wire coil though, because we're just controlling the module that's internal to the coil. So we're going from a 0 to a 5 volt, and this is building up that dwell inside of the coil. And when we're ready to fire this coil, then we turn it off abruptly, and we then have our ignition event.
So one other question with that, Chris. Can we see the ignition secondary pattern on the primary, like what we saw with a 2-wire?
Right, that's a great question. So analyzing this with like a paddle probe is not going to be as straightforward, and that's why I was kind of making a point of that at the very beginning of the class is when we only have the PCM control and a ground supply or a power supply, we're seeing that secondary ignition voltage, and we can see what's happening very easily with a paddle probe. When we're running into the coil having the module internal to it, we're more so seeing just the controlling from the PCM of the ignition module internal to the coil. So we're not going to see the same voltage signature as what we were before.
So basically, if we could open up that coil and separate the module from the coil, that's what we'd have to do. And
exactly. We're on the wrong side of our voltage here. So we are not looking at our high voltage. We're more so just looking at the control of the ignition module that's internal to it.
And a question just came into, how do I know if it's got the internal module or if it's PCM controlled directly?
Right. So a great piece of information here would be everything that I've looked at that we've just shown you has come from service information directly. So this is both from aftermarket, like All Data, Mitchell, anything like that, to OEM data. They will all provide you with this information. And also, you'll see by the wiring diagrams too of what we've got going on, but service information will tell you exactly how this ignition system operates. So some of the things that we've covered here are ignition components, the different ways that they are actually controlled, wiring diagrams, and how the power feed, the ground, and PCM control looks. We've thrown a case study in here to analyze, and then we've also put a lab scope on vehicles in the shop and analyzed the ignition patterns.
Awesome. Thanks, Chris. That was a lot of information packed into a half hour here. If y'all are looking for more information, we've got a ton of different classes out there that cover ignition systems even more in depth. We've got some already available on demand. We've got these in our pro training clinics. We've even got an upcoming ignition class coming out this coming summer. So look at your local parts store, request some standard brand training classes to learn more about this. We're going to post a recording of this class on our standardbrandtraining.com website. Go there and feel free to share it with your friends and neighbors. If you're looking for more about the standard or Blue Streak ignition components and some of the products in our lines and the enhancements we've made to it, always going to recommend you go to standardbrand.com to learn more about any of our products there as well. So we're going to be back again in January after the holiday season. We'll have Peter McCardle back with us to talk about heater cores. It's a very timely presentation for this time of the year, and he's going to share some diagnostic solutions and repairs tips when it comes to heater cores. So Chris, before we take off, any final tips related to ignition coils?
Yeah. One tip that I recommend, I guess, is if we're running into the replacement of a coil or something like that, it's oftentimes best practice to not just replace one coil. If we've got a failure of one, it's likely that the other ones are probably not far behind, and that, they're all under the same amount of stress. And then the other thing also is to remember that not only is it just the coil that may have failed, what caused that. So if it's a worn out spark plug or anything like that too, we're going to want to replace those plugs as well.
So if we had like carbon tracking on the spark plug or something,
exactly,
we don't want to transfer it over to the new boot there. And I can certainly relate to that with my own kids. 2006 Ford Fusion. It was very similar to your case study where the shorted coil burned out the driver in the PCM. And if I'm going to pull the intake plenum to remove one of the rear coils, it's going to get them all,
exactly,
right?
Yep.
Especially as a working technician, you don't want when your customers go through this job, and it's not cheap, right? By the time you replace the PCM and go through all that work, and only to have the next coil fail and do the same thing over. They're going to go, ever since you didn't actually fix my problem.
Yep.
So let's do the job completely upfront. So again, thanks for tuning in. Enjoy the rest of your afternoon here. We look forward to seeing you at the next Power Hour.